Hello everybody and welcome to this week's video. Today we will be looking at I think we've been a bit heavy um, recently with some of the topics, and so I wanted to sort of do something. It's still it parallels things we've sort of looked at before, and I thought it would be quite fun to go through. So what we'll be doing today is looking at the skin effect in a cylindrical wire, carrying an alternating current, and we'll see what we see at the end. Anyway, we can begin with the Maxwell's equations in a linear isotropic. I think it's isotropic that we have to assume, homogeneous medium. And what we'll assume is that time harmonic fields with an angular frequency omega all the fields that have the dependence of e to the I omega t, basically. What am I trying to say? We assume that they have a dependence. Yeah. Right, let's start writing, because if I keep talking I'm gonna say the wrong thing eventually. Anyway, we can start off. I'm going to use H. H here is the magnetic field strength, and B is the magnetic flux density. Is equal to J plus. This is just a different standard form of this. J is of course the same thing here, which is the electric flux density that we're trying to find. No, the current density distribution, and D is the electric flux density. Right, there we go. Cross this with the electric field is equal to minus. This one is standard. Faraday's law. And this is also Ampere's law. I forgot to say that. With the Maxwell bit, which is that. Anyway, we shall continue. Now we have some useful tidbits that give us relations between all of this stuff. So first of all, I think it was Kirchhoff who reformulated Ohm's law into this form, which says that the current density distribution J is equal to sigma, which is the conductivity of the specific material, time, or time, because this would be a scalar, times the electric field, or the electric field strength. And then B, these ones sort of parallel each other a bit more. These are the magnetic permeability and electric permittivity equations. It's definitely that way around, I hope. And D equal to, I don't really like writing my epsilons like that. Epsilon E, where mu is the magnetic permeability and epsilon is the electric permittivity. And now we can sub these. Well, first of all, we sub it into this top equation, the Ampere's law, and we get that the divergence of H is sigma E from there, and then we take the time derivative of this, which is I omega epsilon E, and we can factor that out there. Sigma plus I omega epsilon. Cool. Now we're going to assume a good conductor. So what we can say there is the conductivity is much bigger than omega epsilon, or the displacement current. So we can kind of ignore this term because this doesn't really mean anything. So we can say that therefore cross H is roughly equal to sigma E, which is nice. Doing the same for Faraday's law, the divergence of the electric field is minus I omega mu h. I forgot that. I'm going to be forgetting my arrows a lot. Since I wrote notes in LaTeX, I can just throw it in bold, but it's kind of hard to, do something in bold when I'm actually writing. So, that's what we got. Anyway, now we have some more useful equations. And what we can start to look at is the vector wave equation that we're going to get. So we want an equation just in terms of J, because that's what we're trying to find. So we can multiply Faraday's law by sigma here. So we say that the divergence of sigma E, we probably put that in a bracket just for clarity's sake, is going to be this omega mu sigma h. And we know that J is, so this is just J, right? So from our equation up here, so sigma cross J is equal to minus I omega, same thing, mu sigma h. And now we will curl both sides. So we get, sorry, I keep saying divergence. Every time I said divergence before, I meant curl. Cross J. Trying to revise for history tests and keep all this stuff in my head at the same time is not a very successful endeavor, so it seems. Cross H. German Mail's really got a grip on my brain power. Anyway, of course, from above, we actually have that this is equal to J. I never wrote that in, so the second curl of the current density is minus I omega mu sigma. I can just write J in there, which is useful to know, and actually this just becomes the Laplacian, minus the Laplacian even, by the continuity equation. And the net charge density in a good conductor just dissipates, free charge dissipates almost instantly, so net charge density is about 0. So the divergence of J is equal to 0 as well, which just leaves us with this being minus the Laplacian of J. And again, that's equal to I omega mu sigma J. Yeah. Cool. And we can throw this all onto one side and make it equal to 0. Minus, let's be plus I omega mu sigma J equals 0. Nice. What am I on about? Oh, I am on about the right. What? Oh yeah, wait. Why have I written it like that? Stupid thing. No. Oh, why? No. There we go. Stupid thing. There we go. Don't mess up my signs. I think we ought to clean this up a bit, so I'm gonna define a propagation constant to get rid of that, which is gamma, and we'll say that gamma squared is equal to I omega mu sigma, because then it looks pretty, and also it will help us in a minute, which yields the Helmholtz equation, which is, as written, also because Helmholtz wrote it like that. Did he? Yeah, no, he did. Because then it works out. Okay, so this is good so far. Now we're going to change. We're going to go into cylindrical coordinates, as you do when you're working with cylindrical stuff, like cylinders, like cylindrical wires, which is horrible, but it's okay. We can persevere. So since current will only flow in the z direction, we know that it only has a z component. So we can say that j is equal to some jz r phi, not theta, phi z times the normal in the z direction, or rather the unit vector. And by symmetry in a cylinder, current can't depend on the azimuthal angle, so by and also it doesn't depend on z because it's an infinitely long uniform wire. So it's actually just a function of our radius. So we can say that that's not really equal to it. I shouldn't say that, but then that's okay. R times the unit. Now we can expand the Laplacian from above into these cylindrical coordinates, which is going to get a bit messy. So we're going to do it like this. Is 1 over r times the ddr of r djz dr plus the same thing kind of squared for phi, and okay, 1 over r squared jz over partial phi squared plus jz partial z squared. Oh, cool. And our symmetry conditions again make this slightly trivial because that's equal to 0. That's also equal to 0, so we lose both of those. And hence this is just d squared jz dr squared plus 1 over r djz over dr, just from expanding that. Yeah. Why do I keep writing a half? Oh dear. That's alright. And we can throw this into our Helmholtz equation that we didn't get that long ago, up there. And we get that minus gamma squared jz equals 0. And we end up with something quite familiar to anyone who's taken or watched my other videos, or for that matter, anyone who's taken elementary quantum physics or even chemistry or pretty much anything along those lines. You might know what this is. This is a parametric form of Bessel's differential equation. We can make this a bit more obvious by performing a change of variables. I'm just going to use u equal to gamma r, so r is u over gamma, and hence djz dr is equal to dj using chain rule u cool d squared jz dr squared is equal to d dr gamma djz du from above, which is gamma d du times du dr, which is gamma squared, yeah, d squared jz d squared. Cool. Because of course we know what that is. We know what that is, rather. Right. Nice. We can sub this back into our not so nice equation to get a slightly more obvious one. D squared jz over du squared plus... I forgot gamma. Someone's confused. Gamma over... It should actually be gamma over u over gamma times gamma. That's a bit messy. I'm going to leave it like that, though. Just for the sake of it, because it'll make it more obvious. In the next step, where we divide everything by gamma squared and multiply by u squared instead, we get that u squared d squared jz du squared plus u djz du minus u squared jz 0. I always think these kind of look like quadratics, but like differential equation addition. It is quite a common non-trivial differential equation to learn. So I guess they're going to make sense. Anyway, this is just the Bessel differential equation of order 0. And we have a general solution to this, which is a linear combination. Yay, linear! Linear combination of Bessel functions of the first kind and of the second kind. I read that those are also called Neumann functions. I'm not going to call them that. I'm going to call them Bessel functions of the second kind because it's a funnier. Like, of the second kind. Not the second Bessel functions or something of the second kind. Anyway, so our general solution to this is ej0, where that's our Bessel function of the first kinds, plus gamma r. Okay, so we know that the Bessel function of the second kind diverges to negative infinity at the origin, because that's just kind of how it is. You can write that as the lim as r towards 0, y0 of I gamma r approaches infinity, which is annoying because at the center of the y the current density must be finite. So we have to set b equal to 0, which is actually not annoying, because it makes it even simpler. So we know that it's now just some variable a times j0 I gamma r. So there's only one Bessel function involved, which is nice. Anyway, let's sub in some a. A is going to be our diameter. No, radius. Of our real wire to get it to get an output in terms of a. That's a little a, by the way. So j sub z of a is equal to a j0 I gamma a, which is just js, alright, which is the current density of the surface. And from this, big A is equal to js over j0 I gamma a. Cool. and we can substitute this back to give an exact distribution. So J sub Z of R is equal to JS times a fraction J naught I omega R over J naught I omega A. So this is pretty good. This is our distribution where Js is the current density of the surface. Js is the current density of the surface. J naught is goodness me. Can't concentrate. Okay, so Js is, so that gives us this distribution where Js is the current density at the surface, and J naught is the Bessel function of the first kind, where R is some radius. Now we can interpret this physically because it's quite abstract at the moment. So let's unpack. We remember that gamma squared equals I omega mu sigma. Thus gamma is square root of I square root of omega mu sigma. In polar form, I is e to the I pi over 2, and the square is e to the I pi over 4, which is cos pi over the 4 plus I sine pi over 4, which is a half plus I times a half, which is 1 plus I over 2, root 2 even. Why did I say half? 1 over root 2, or root 2 over 2, plus root 2 over 2I. So that would actually be 1 plus I over 2, yeah. Or root 2, 1 plus I over 2. But I'll leave it fixed. So then this is 1 plus I over root 2 root omega mu sigma, which is 1 plus I. Yeah, this is why, because then we can bring it all in the bracket. Mu sigma over 2. And this is somewhat reminiscent of the definition of skin depth, which we define as delta to be the root of 2 over omega mu sigma. And so gamma is just 1 plus I over delta. And this could be plugged into the main equation, which I'm not going to do, but it could be done. I do have a more useful form of this written in my notes. They're very, the notes, they're sort of quite sporadic, so apologies if I seem disjointed at times. I'm sort of, bits of it I know, and then bits of it it's like, oh, what do I do? But I do have the general things written down. And here's one. So if we use an asymptotic expansion of J sub 0, the first Bessel function of the first kind, for large arguments, the current density decays exponentially from the surface. And we can write that mathematically as J sort of R is roughly equal to Js, that being the current density of the surface, times e to the minus R. I'll actually put that a minus R over yeah, that's all right. And this shows that there's a relationship here, but obviously between omega and delta. So as omega increases, the skin depth decreases, which sort of forces all of the current into, if you think of a wire, if we have low angular frequency, low omega, and then high omega, you sort of have like, I don't know how I draw it. You sort of have like this kind of thing where it gets more and more, but there's a bigger delta. They're just more spread out, whereas on this it might be like that. So delta's much lower. That's delta high, sorry. But obviously they're a lot more concise and closely packed together. The current is, which is interesting. I always find it weird, and if, I don't know, anyone who's got to the end of this video probably isn't going to be asking this question, but I'm sure anyone might, if you are asking this question, why is it useful, or why does anyone care? I was building for my GCSE DT project. I was building a induction heating portable device, and as part of that, I forgot to box it. I'm gonna box it now. As part of that, I needed to calculate the skin depth through the big old piece of metal that I was trying to heat up, to see how much it would heat up on the edges as opposed to the internal heat, which didn't really matter that much. It was more just to get a more accurate model of how it would heat during my planning stage, so I could work out what I wanted to put inside of it. Very engineering kind of thing. Sorry, pure maths, pure physics people. Anyway, I ended up doing this and using this back then, and I put it all very beautifully, and then I got told that there was too many words in my doc, so I had to remove it. So that was funny, but it's fine, and the project ended up working. So yeah, crazy numbers, and in fact there's probably not many numbers, crazy letters all over the place actually come in useful for the first time ever. Anyway, on that note, I hope you enjoyed the video. I hope you found it interesting to find a very visible result from this one, which I quite like. Probably much less heavy than the stuff that's been going for the last couple of weeks, so that was nice. Might get back to it again next week, but that's alright. Anyway, see you then.